Good evening. I am about to borrow from another YouTube channel, a more entertaining YouTube channel called Beyond the Press. It's a guy somewhere in Russia, I think, post-Soviet Russia, and his favorite pastime appears to be to smash things, blow things up, get them spinning super fast, which is the content of this video. So he's got a bicycle wheel mounted here, and I guess he was curious whether the rubber of the tire would explode or melt, or maybe the bearings, if he gets this thing spinning at 30,000 RPM. Is that even possible? Let's find out.
And here we go. Oh no! The wheel was too heavy for the motor.
When I decided to put that clip in this presentation, I hadn't even noticed that he actually gives us some numbers there. He states the rotational speed of the wheel and the so-called linear speed of a point on the rim. And he probably did that using an equation that we'll develop here. So we'll have to go back at the end and see if we can confirm those numbers. So here's the bicycle wheel that he got spinning. And let's pick a representative point somewhere on the tire. Now, we know that this point on the tire is moving in a circle because, well, the bicycle's rotating, so that's fairly obvious. And we also know that the velocity vector of a particle in motion at any instant is tangent to the trajectory. So since the trajectory in this case is a circle, we need a vector that's tangent to the circle in order to represent the velocity. And remember, we use the length of the velocity vector to mean its speed. That's what speed is. It's the magnitude of the velocity vector. So for a moment, let's ignore the fact that as this particle moves in its circular path, its velocity vector is always turning. We've already looked at that a few presentations back. We talked about centripetal acceleration, or maybe that was one presentation back. So we know that the velocity vector is turning. But for now, let's ignore that aspect of the motion and focus on the fact that because the bicycle is currently spinning faster and faster, it's accelerating as far as its rotation is concerned. That means that this particle on the tire is moving faster and faster. So some small moment in time later, or I should say some small time interval later, this particle has moved a little bit, and I've now made its velocity vector longer to signify that it's moving faster. So here's the original velocity vector with the given length. Some small unit of time later, it has sped up, and I'm representing that with a longer velocity vector. So let's call those the initial and final velocity vectors over this tiny time interval dt, which is like an infinitesimal delta t. And as usual, we can use the label d theta for the tiny angle swept out by that particle. And now we're finally talking about what is often called non-uniform circular motion. The non-uniform merely means that the speed is not constant. You're either speeding up or slowing down, or speeding up and then slowing down. The simplest type of circular motion would be uniform circular motion, in which the speed is constant. Pardon me. So what I've done here is scoot my two velocity vectors over. Remember, you can do that. Vectors are movable, aroundable, scootable, overable. The only requirement is that you keep their length and direction the same. So this was the velocity vector when the particle was at the bottom here, and then some small time later it's moving a little bit faster. That's at velocity, or the velocity at time t plus delta t. Now we've spent quite a bit of time at this point visualizing vector addition and vector subtraction. Hopefully at this point you're familiar with this equation. Final velocity is initial velocity plus the change in velocity. Another way to think about this would be to rearrange. If you subtracted v of t from both sides, you would have v final minus v initial equals dv, in other words, the change in velocity. But I've chosen to write it in terms of vector addition, and you can also see that's what's drawn here. I have placed the initial velocity vector tip to tail with the change in the velocity vector. And when we add these tip to tail, of course, this is their sum. So you can see how the final velocity is the sum of the initial velocity plus the change in velocity. In this case, delta v, or dv, if you want to talk about infinitesimals, dv points in the same direction as the velocity vector. That is different from the case of the centripetal acceleration that we just discussed already, where the acceleration pointed towards the center while the velocity was tangent to the circle. Now we're looking at a dv that's parallel to, or in the same direction as the velocity vector. Well, once you have determined graphically the direction of dv, now you know something about the direction of the acceleration vector, because remember, how do you get from change in velocity to acceleration? By definition, acceleration is the rate of change of velocity. So it's just delta v, or dv, divided by dt. dt is a scalar, dv is a vector. So we know that dv then points in the same direction as the acceleration vector. All you've done to dv is scale it by multiplying by 1 over dt. That does not change the direction of a vector, that only changes its length. So just like the centripetal acceleration case, if you can figure out in this instance what the direction of dv is, or delta v, now you know the direction of the acceleration vector. And in this case, it is not towards the center. Keep in mind, I'm ignoring the fact that the vector turns. We find that there is an acceleration tangent to the circle. That's something you want to memorize. Anytime something is in circular motion where it's speeding up or slowing down, in other words, non-uniform circular motion, there must be an acceleration tangent to the circle. We'll get back to the fact that there's also a centripetal acceleration just by virtue of being in a circle. If you're moving in a circle, you're turning all the time. So there must be an acceleration towards the center. But if in addition you're speeding up or slowing down, there will be a tangential acceleration. And notice that the tangent vector that I'm calling a for acceleration points in the same direction as the velocity. And in that video, the particle is speeding up. So when a particle is in non-uniform circular motion and it's speeding up, you can expect the acceleration vector and the velocity vector to point in the same direction. Which makes sense because when we get to Newton's second law, F equals ma, we will see that acceleration and force are proportional. They always point in the same direction. How would you get something to speed up if it's already moving in this direction? Wouldn't you have to push on it in the same direction? If you push on something in the same direction it's already moving, you will cause it to speed up, and that's why we see an acceleration in the same direction as the velocity. Acceleration and force, same direction. Okay, so your book chooses to call this a tangential acceleration. You might also call it a transverse acceleration. I'm sure other terms exist. We will go with tangential acceleration for obvious reasons, right? That vector is tangent to the circle at that point. So a quick look back at the other acceleration which must exist for a particle in circular motion. We saw that because the velocity vector is turning, when you look at the direction of dv, you find that it points towards the center. So this was for the case of uniform circular motion. If I've drawn v1 and v2 with the same length, that would indicate that the speed is not changing. So the direction of the velocity vector is changing, but its magnitude, in other words, the speed, is not. If that's the case, then the acceleration vector points purely towards the center. It has no component tangent to the circle, it's only towards the center. Hence the name centripetal acceleration. That sounds awkward. Okay, let's change the notation slightly. Instead of v1, v2, remember these two velocities are separated in time by an infinitesimal time interval. So how about the initial time I just called t, and the later time is t plus delta t. So the initial velocity is v of t, the velocity at that later time is v of t plus delta t. And now what I've done, if you look carefully, is to intentionally make the second vector quite a bit longer than the first vector. That's a little unrealistic because how much can your speed really change during an infinitesimal time interval? Well, that would have to be just an infinitesimal change in speed. So it's a little unrealistic that I made this vector so much longer than this vector. But that's to help you visualize things. So let's just pretend that this one's just a little bit longer than this one. And now I've placed them tail to tail. Tip to tail is for vector addition. Tail to tail is good for visualizing the difference in two vectors. So change in velocity, remember that's final minus initial. This vector, this blue vector, minus this vector, is a third vector that points from the tip of this one to the tip of the other one. I'm sure there's a better way to word that. Hopefully at this point you totally understand how to see vector subtraction. Or again, you could write it, as we did before, in the form of a vector addition. Initial velocity vector plus the change in the velocity vector gives you the final velocity vector. Notice how v of t and delta v are tip to tail, as they should be if you're going to add them. So what have we discovered? As soon as you can see the direction of delta v, you also know the direction of another vector. What is the vector related to change in velocity? Of course, that's acceleration. So a finite delta v over a finite time interval, that's what we call average acceleration. So technically, delta v over delta t is the average acceleration during a time interval. But if you then let that delta t go to 0, make it a teensy-weensy delta t, in which case we call it dt. Still means change in time, but it's a teensy-weensy infinitesimal change in time. In that limit, as delta t goes to 0, this average acceleration becomes an instantaneous acceleration. And evidently, this acceleration, because remember, delta v points in the same direction as acceleration, it doesn't point merely towards the center or only tangentially. It seems to have two components. So what I've done here is, if you observe, maybe you should tilt your head a little bit. Can you see that this vector A points in the same direction as delta t? Remember, what happens to delta v as you let delta t go to 0? As delta t goes to 0, the change in velocity also goes to 0. Your velocity can't change by much in a thousandth of a second, or a microsecond, or a nanosecond. So the length of this delta v vector is shrinking as delta t is shrinking, until there's practically nothing left. But the idea is, if you let this get smaller and smaller, but you continue to divide it by something that's also getting smaller and smaller, you actually approach a limiting vector, in this case, that is not 0. That's the whole notion of a derivative. It's a limit. The numerator is going to 0, the denominator is going to 0, but the ratio of the two does not. In fact, it's approaching a particular vector called the acceleration vector. But at the very least, you need to see that this vector A has the same direction as the vector in the numerator in the limit as delta t goes to 0. Okay? So the whole point here was to draw the initial velocity and the final velocity, look at their difference, which we call delta v. As soon as we have determined the direction of delta v, now we know the direction of the acceleration vector. And we've also had plenty of practice with resolving a vector into components. Remember the rule. You make a right triangle where the original vector is your hypotenuse. That is how you resolve a vector into components. And here's a very slight change in notation. I may have previously called this a sub c for centripetal acceleration. You can see that it's centripetal because this points towards the center of the circle. But your book prefers usually to call it the radial acceleration. You can see why that component is along a radius of the circle. So if it's pointing towards the center, we'll call it the radial component of acceleration. And the tangential component is here. You may be a little confused when you look at that because you're thinking, hey, wait a minute, the tangential component should actually be tangent to the circle. Well, remember, vectors can be moved around. So if you take this tangential component and scoot it up there, then you see obviously why it's called tangential acceleration. Okay, so you can draw it like that, you can draw it like this. This way is probably easier if you're just eyeballing it because you can see the triangle in your head. But when you draw it like this, it's easier to understand why those two components have the names that they do. But you want to understand that if you think of this as its own vector, this vector plus this vector is the same thing as this single vector. So we have resolved the net acceleration into its components, and really we're talking about its components along two special axes. Instead of the x-axis, which is horizontal, and the y-axis, which is usually vertical, I've chosen an axis that passes through the origin, or I should say through the center of the circle, and an axis which is perpendicular to that. Now if you think about it, as your particle goes around and around, if this component is always pointing towards the center, then isn't this axis changing? The axis that passes through the center of the circle, that's centered on the particle, well, I should say the origin is on the particle as it goes around the circle, and the radial axis, must pass through the center. That axis is actually rotating itself. Okay, so what can we conclude, again, if the tangential acceleration is in the same direction as the velocity? So here's a particle that's going counterclockwise around the circle when viewed from the front. Note that if you could go to the back side of the circle and look back at the particle, you would actually see it moving clockwise. That's kind of interesting. So in this case, the acceleration points in the same direction as the velocity. Remember the rule, if you're pushing something in the direction that it's already moving, you're causing it to speed up. So in this instance, the particle would be speeding up. On the other hand, if the tangential acceleration were opposite the velocity, that would be equivalent to a push or pull backwards, opposite the direction that the velocity points. You would expect that particle to be slowing down. How do I know that there's a radial acceleration that points towards the center? That's always true for an object in circular motion. And remember that formula, v squared over r. The faster you go around the circle, the longer this component gets, because the magnitude of this component is v squared over r. Well, there's really nothing new here. It's not like you have a new formula that you have to memorize. Any vector, the magnitude of any vector, can be found using the Pythagorean theorem. A vector with two components, it's perfectly valid to apply this form. I shouldn't say it's perfectly valid. This is how you would do it. You would square each component, add them up, take the square root, right? That's just the formula for the hypotenuse of a right triangle. And when you resolve a vector into components which are perpendicular, you're looking at a right triangle. So different books might use different notation here, but there's really nothing to memorize. You just have to understand the way in which the acceleration is resolved. One component through the center of the circle, one component tangent to the circle, and then once you see that right triangle, you know how to use the Pythagorean theorem to get the hypotenuse. Because what is the hypotenuse here? It's the magnitude of the net acceleration vector. That's why I've chosen to write it this way. Now, I could have just written the letter A without the vector symbol. Remember, in this book and many other physics books, when you write the letter for a vector but you don't include the arrow, you're talking about the length of that vector, which in this case means the magnitude of the acceleration. Okay, let's turn back to our some of our trig review that we looked at, the relationship between arc length, a tiny little angle, and the radius of a circle. This is really the definition of an angle in radians. How do you compute the size of an angle in radians? You just take the arc length intercepted by that angle and you divide it by the radius. So if I had to estimate here, I'd say ds is something like 1/4 of the radius. If that were true, I would call this angle 1/4 of a radian. Now, it's not really appropriate to call it ds and d theta for such a finite distance here. The idea is that the angle d theta and the length ds are infinitesimal. Of course, if they really were infinitesimal, we couldn't draw them in the slide. Move the r over, and you get this form of the equation, which you should really memorize. All it says is, let's go back to that particle on the bicycle wheel that's going around and around. During a small time interval, dt, infinitesimal time interval, if that particle moves through an angle d theta, if it sweeps at an angle d theta, and the bicycle has a radius r, if you just multiply those two quantities together, you will know the actual distance traced out by that particle. Right? Maybe you just put a little a dot of white paint on that bicycle wheel. If it sweeps through an angle d theta, ds is the distance in space, like in meters or inches or whatever, that it traced out. And now let's do something clever that's often done in these physics derivations. It may seem arbitrary at first, but it will lead us to another very useful equation. Let's divide both sides by dt, which is really the same thing as taking the derivative of both sides with respect to time. That's actually what I've done, is to differentiate both sides with respect to time. But you can also think about it as dividing by dt if you regard the derivative as the ratio or a fraction with two infinitesimal quantities in it. So now let's figure out what this equation is really telling us. ds over dt, ds divided by dt, what is that quantity? Well, ds, the numerator, that's the distance traveled by that dot of white paint on the wheel. That's the distance it travels through space, and dt is the amount of time it takes to do that. So if you think about the units, the SI units would be meters over time, or maybe you were measuring distance in inches per time, centimeters per second. If you were measuring distance in miles and time in hours, you'd have miles per hour. Aha! Everybody knows that miles per hour is the unit that you use, well, at least here in the States, it's the unit that you commonly use for speed. So that's really what we're talking about. ds dt is the rate at which distance is being covered or traversed by that dot of white paint on the bicycle wheel. I guess in the picture it was yellow paint, wasn't it? Okay, and the obvious choice for the name of that quantity, which is v for speed. Remember, the letter v without the vector symbol really means the magnitude of the velocity vector, which is what we call speed. Now what about d theta dt? We figured out what the left-hand side of this equation is, but can we assign meaning to this quantity? Well, just like before, it's obviously some kind of rate, change in an angle this time over a change in time. And we know about how derivatives work. d theta dt is really the same as change in theta over change in time, delta theta over delta t, in the limit as delta t goes to 0. So it's the limit of an average rate of change. Radians per second. Are there some other units we can use there? That would be the SI unit. And I should point out right here that technically a radian is not a dimension, or I should say it's dimensionless. How do we know that? Well, over here is how we define an angle in radians. What is the dimensionality of the right side here? Distance is measured in meters, and radius is measured in meters. Meters over meters is dimensionless. So you want to memorize that when you're talking about an angle in radians, you're really talking about a dimensionless quantity. That's also true for degrees. Degrees are dimensionless, it's just an angle. You could also think of it this way. An angle is what you plug into the sine function, cosine, tangent. Those are dimensionless quantities. You don't plug meters or seconds into a cosine function. You plug a dimensionless number in. Now what about, degrees per second? That's a perfectly valid, if you think about the yellow dot on the bicycle wheel going around and around, you could ask yourself, how many degrees is it sweeping out per second? Like if it takes 1 second to go around a full revolution, then it would actually be tracing out 360 degrees per second. That's not very fast. It's certainly not as fast as what you actually saw in the video, but that's all it means. It's just how many degrees, what angle are you tracing out per unit time, per second? You could also do it in revolutions per minute. You could ask, how many full revolutions does this thing execute in 1 minute of time? Rev per min. Now, if it goes through, just easy example, if it goes through 1 revolution every second, wouldn't it be going through 60 revolutions every minute, since there are 60 seconds in a minute? So it would be 60 RPM. Most of you are actually familiar with this unit of angular speed, so I neglected to use that term yet, but that's really what we're talking about. ds dt, that's just regular old speed. How quickly are you moving through space? Now we're talking about angular speed. What's the the rate at which you're turning through an angle. And RPM is a very common unit for that type of speed. Now let's watch the Let's watch the slow-mo guys get an old record up to some extraordinary rotational speed, and they're recording it at 12,500 frames per second. That's got to be an expensive camera. But there's a nice graphic here because they've painted the record so that each quadrant has a different color, and it's very easy to see the rate at which the angle is being swept through.
Yeah. So it's really at the limits of...
It's hungry.
Yeah, it really is.
Hungry lad.
Yeah, it was another crack from the outside, that one.
Shall I see?
Yeah.
So there it is. Just pick the boundary between two colors like this one and watch, try to imagine the number of degrees per unit time that it's sweeping out, or radians per second. That's all it is.
Wow. It looks cool with the colours, doesn't it?
It's like a really convoluted way of...
As I mentioned, perhaps the most familiar unit for angular speed would be the revolutions per minute, often abbreviated RPM. And if you look at the dial on a dashboard, I think that's called a tachometer. There's the speedometer, and then to measure the rate of rotation of the input shaft in your transmission, I think they call that a tachometer. And obviously, that input shaft is rotating more than just 5 times per minute, right? They've got the numbers 1 through 8 on here, and we're talking about revolutions per minute. 5 revolutions per minute would be nothing, right? Which is why they've indicated times 1,000. So 4,000 RPM, 3,000 RPM, that's a typical rotational speed for the input shaft into your transmission when you're just cruising. If you're idling, if you're at a red light and you put your car in neutral, or let's say you've got an automatic transmission and you're just sitting there, it's probably down at 2 or lower. And some of you guys know way more about this than me. But inside the transmission of your car, here's a manual transmission. I've just been watching videos lately about how these things work. Whoever came up with this was super clever. It's just amazing how this all works. But what's this? The clutch disc connected to your engine here on the left. And yeah, evidently it's rotating thousands of times per minute, which is why it's so darn loud unless you have a muffler on that thing. Maybe an even more familiar rotational speed is this one, the speed at which the Earth rotates. How many RPM is the Earth turning at? And I have to tell you, when I look at this graphic, I'm reminded of a soap opera that women in my family watched when I was a kid. I don't even know if the soap opera is still on, but it's been around. It was around since like the 1940s. I don't know. As the World Turns. I can't look at this graphic without thinking of the theme music for As the World Turns, followed by some scene of intense family drama in the show. You know those shows, what they're all like. Okay, so we use the letter omega for angular velocity. That's pretty universal. It's not a W. It looks like a W, but it's the Greek letter omega. It's like a rounded W. Which actually, I mean, if you think about it, the letter or the name W, shouldn't that mean that it looks like 2 U's drawn next to each other, a double U? Whereas usually when we write the letter W, it looks more like a double V. Double V, that's what they should call it. TUV, double V, XYZ. This one actually does look like a W, but we don't call it a W. It's the Greek letter omega. Okay, if you measure angles in revolutions, you could do that, right? Like a unit of angle could just be a full revolution, which is known as 360 degrees, which is the same as 2 pi radians. But a revolution is a valid unit of angle. It just happens to be the same as 360 degrees. And then you could measure time not in seconds or minutes or hours. You could measure it in days. And then in that system of units, the rotational speed of the Earth takes on a really simple value. It's the number 1. Easy, right? That the angular speed of Earth is 1 if you're measuring angles in revolutions and time in days, because it does turn once in a day, roughly. It depends on your definition of the day, actually. Now, if you were going to express this speed in degrees per day, you would say 360 degrees per day, or 2 pi radians per day. So how many radians does it turn through in an hour, or a minute, or a second? Well, that's just a simple matter of conversion. So you could divide by 24 hours for every day, divide by the number of seconds per hour, and then lastly, let's convert from revolutions to radians. Again, a revolution is a valid unit of angle, but let's deal with the radian instead. Remember, 1 radian is about 57 degrees. So there are 2 pi radians for every revolution, and we wind up with this very small number. Not surprising, right? It takes a whole day for Earth to turn through 2 pi radians, and 2 pi is close to the number 6. So in an entire day, Earth turns through about 6 and some change, a little bit more than 6 radians. So how many radians will it turn through in 1 second? Not very many. It's this very small number. What is that? 70? That's basically 73 millionths of a radian. How about that? Every second of your life that passes, you've just turned through 73 millionths of a radian. There went another 73 millionths. There's another 73. Can't get those back. Okay. What about the moon? Just as another example. It takes the moon a full month to rotate once. Maybe you're thinking, I thought that was how long it takes to go around the Earth. And that's true. It does take the moon about 1 month to go around the Earth. But it also takes the moon about 1 month to turn on its own axis. And as a result, the moon is always facing the same side to us. So this graphic is not what you would see from planet Earth. We only ever see one side of the moon. If you want to see the other side of the moon, you've got to get in a spaceship and go way the heck out there. And I remember hearing in a documentary with some of the Apollo astronauts that they were kind of disappointed when they got to the back because it's a little boring back there. Thankfully, the interesting side of the Earth is facing us with all the craters and what they call the Maria. And there's probably a reason for that, right? That can't just be a coincidence that all the good stuff is facing the Earth. Maybe that has to do with how the moon formed. Okay, so back to the relationship between all these quantities. We have a name now for d theta dt. Angular speed, we abbreviate with the letter omega, which does look like a double U, but we don't call it a W. Okay? And that means we can rewrite this equation. So we've now established that ds dt, that's the rate at which you trace out distance around the circumference, that's just speed, and d theta dt has this name omega, and you have now arrived at one of the top 10 equations that you'll need for the entire semester. That's no exaggeration. If I had to make a list of 10 equations, I'm fairly certain that this one would be on the list. V equals r omega. So I'm putting a special blue box around it. This equation tells you how to convert for an object in circular motion, I should say a particle in circular motion. It allows you to convert between angular speed and linear speed. How fast are you actually moving through space in miles per hour or meters per second? Well, you could just take the rate at which you're spinning or turning and multiply that by the radius of the circle. Your book and other books choose to put this subscript t next to v. Any idea why? Why would we put a little t next to this velocity vector, which is tangent to the circle? Right, we're emphasizing that the velocity vector in circular motion is tangent to the circle. I won't always put the t, even your book doesn't always, they're not always conscientious enough to put the t, but it's not really necessary. Whether you write it this way or this way, as long as we're talking about circular motion, it's the same thing. Now, if you're wondering, what's the point of even distinguishing tangential velocity? Like, if there is no other velocity, what's the point? Well, it's because in many applications, for instance in astronomy, something that you're looking at isn't just moving in a circle. So consider our solar system. Here's the sun, and the planets have not been indicated here, but just imagine all those little planets in our solar system orbiting the sun, and then there's this vast amount of empty space between us and the next star system. So here's a very far away star. We're talking, I don't know, 20 light years away, and it's got some overall motion relative to the sun. So maybe that star is drifting off in this direction. From our perspective, back here in the solar system, when you look at that star, it's convenient to resolve the motion of that star, or the velocity, into two components, one of which is perpendicular to the line of sight. This is the line of sight. If we're here looking at the star, that direction is the line of sight. So that star has some motion towards us. That's what's called the radial velocity. And it also has some velocity perpendicular to that radial velocity. So again, we're just resolving a vector into two components, much like we did with the acceleration a moment ago. So just be aware that if something is not moving really in a circle, you could decompose the velocity in that way. Right now we're talking about circular motion. If this star really were making a giant circle around our solar system, then wouldn't it have no radial velocity? It wouldn't have any component along the radius, in which case the net motion would be the same as the tangential velocity. So if you're actually moving in a circle, vt and v, they're the same thing. Let's look at somebody else's video.
In this example, we're looking at a disk which is going to rotate at a constant angular velocity of 2 radians per second. It is special to note that the angle must be measured in radians. This will not work if you measure it in revolutions or degrees, so you will have to convert back to radians. Now, we've placed points along the disk at 0.5 meter intervals from the center of the disk out to the radius. These points are to allow us to measure the velocity or the tangential speeds at those locations, because what we'd like to know is how does that relate to the angular velocity of the disk itself. Now again, this is a rigid object, so these points are not allowed to move differentially with respect to each other. They have to be locked into the same pattern. So let's get started. Right off the bat, you notice that the outside point has to be moving at a faster speed than the inside point, because the outside point obviously has a greater distance or circumference to travel than the inside point. So let's see how that relationship actually breaks down mathematically. And right off the bat, you'll see that it's linear. I mean, look at this. It goes from 0 to 0 to 0.5 to 1 and 1 to 2. In fact, it relates in a very easy way. It's the angular velocity times the radius gives you the tangential speed. That's the equation. That's all you have to do. In fact, if you want to go from tangential speed to the angular velocity, well, all you have to do is divide by the radius. So it's a very simple linear relationship between those two things, the angular.
Notice he's chosen to write the order of the factor is different. He's got omega first and then r. Your book likes to go r omega. Same thing. And just a moment ago he said that the relationship was linear. That's because you see an r to the first power here. It's not v equals omega r squared. It's not v equals omega over r. It's certainly not something like e to the r. This is a linear relationship. So if you are twice as far, he's illustrated these various points on this rigid disk. If you're twice as far from the center, you would have to be moving twice as fast. Now that's not the same, that's not necessarily applicable for, let's say, sprinters, track athletes running around a track. The one on the outside doesn't have to be moving twice as fast as the one halfway out because they're not rigidly connected. This would be for something like a carousel, also known as a merry-go-round. You know it, they've got them at various amusement parks. The little plastic horsies you can sit on that make circles around the center here. If you're on the horsey at the edge, you are moving faster than your kid sister who's on a horsey towards the center.
Speed and the tangential velocity, or I should say tangential speed. So that's it.
I don't know what's up with that name there, dropping Anvils. Okay, I did it again there. I just spoke for about a minute and had it on mute. Oops. You'll notice that he's chosen to write this equation with the factors in a different order. He's got omega first and then r. That doesn't matter, right? Aesthetically, your book likes to go with r first. But if you recall, he said that these two had a linear relationship. What does that mean, linear relationship? Well, if you were to plot the speed of these various points that he's illustrated versus their distance from the center, those points would fall on a line, hence the name linear relationship. The angular speed would be the slope of that line. So it's not v equals r squared or v equals omega over r or the sine of r or anything like that. It's just r to the first power. That's what we call a linear relationship. And it tells you that if you go twice as far from the center. And we're talking about particles belonging to a rigid object. See how everything was rotating together? If you're twice as far out, you're actually moving twice as fast through space. So that would not apply, for instance, to track athletes running around a track. There's no reason why the person at the edge of the track has to be moving considerably faster than the one towards the center, because they're not connected. That's not a rigidly rotating object. Those are two independent people. But if you're talking about something like a carousel or a merry-go-round, I'm sure many of you have been on a carousel at an amusement park, and if you're sitting on one of those little, they've got the plastic horses and sea dragons and all those, they're mounted on those poles and the whole thing rotates with the old-timey music. If you're on one of the horses at the edge, you are moving faster through space than the person towards the center, because I think they're all mounted on the same platform, as I recall. Now, a surprising result is something we'll look at towards the end of the semester, which is the planets going around the sun. If these various dots represented the planets in orbit around the sun, it would not be the case that the one at the outer, the one at the outer edge has to move faster than the one halfway out. In fact, it's a qualitatively opposite result. The farther out you go, the slower the planets move through space as they orbit the sun. That shouldn't be too surprising, because it's not like all the planets are mounted on some rigid disk where everything has to turn together. But this was puzzling to early astronomers. What's the reason for why the outer planets move slower than the inner ones? And the first person to quantify that relationship was Kepler. So that's Kepler's third law, and we will look at that later in the semester. Let's collect our two results relating what you might call linear quantities to angular quantities. This equation is really just the definition of an angle in radians. Remember, an angle in radians is calculated by taking the arc length that it intercepts and dividing by the radius. I took the time derivative of both sides, or I divided both sides by dt, to get to this equation. Tangential velocity is related to angular velocity merely by the presence of this factor r. And as the guy emphasized in that dropping Anvils video, this equation only works if you're measuring your angular speed in radians per second. It could actually be radians per minute. If this was, let's see here, let's go with hours. If this was radians per hour and this was miles, then your speed would come out in miles per hour. That would be fine. But the important thing is that the angular part of the unit, or of the dimensionality, is radians. It's got to be radians. If you want to do degrees per second or revolutions per second or revolutions per minute, you can't use this equation. It must be radians. Let's go even further now. We got to this equation by taking the time derivative of this equation. What happens if we take yet another time derivative? So I will differentiate both sides with respect to time. And what have I done here? ddt of tangential velocity. What does it mean to take the rate of change of velocity? Well, we know what that is. We've been talking all semester about change in velocity, rate of change of velocity. That's what we call acceleration. If your tangential velocity is increasing, that's an acceleration. You'd be speeding up, possibly. We'll look at that in a moment. If your tangential velocity is decreasing, you would also be accelerating. And in that case, you might be slowing down. So that's really what we're talking about on the left side. That's just a general result, right? That the time derivative of velocity is something we call acceleration. What have I done on the right side? If you're moving in a circle, then your distance from the center of the circle doesn't change. That's the definition of a circle. So r is a constant. And you remember from first semester calculus that if you take the derivative with respect to x, for instance, of c times f of x, that constant c can be brought out front. That's all I've done. So just pass that constant radius through the derivative, and we're left with this expression. Now, can we do anything with this? This is the rate of change of angular speed, or angular velocity. I should really say angular velocity. So this is the rate at which your angular velocity is changing. What should we call that? Again, anytime we're talking about a changing velocity, we like to think of that as an acceleration. In this case, it's the rate of change of an angular velocity. So you can answer this yourself. What's the best name for the time derivative or rate of change of an angular velocity, that would have to be an angular acceleration. There it is. So it's an angular acceleration is when something is rotating and the rate of rotation changes. It starts to spin faster or spin slower. That's an angular acceleration, which is exactly what you saw in the video at the beginning of this presentation. That bicycle had a very large angular acceleration. So we can now rewrite this top equation. We've identified the time derivative of tangential velocity as tangential acceleration. It's the acceleration of the particle in meters per second along that tangent direction. And d omega dt, we will abbreviate with the letter alpha. That's a new quantity that you need to memorize. Alpha, notice not A, this is a script alpha, or a Greek letter alpha. It's the time derivative of omega. It's an angular acceleration, hence it's the time derivative of an angular velocity. We can take this result now, we'll put a box around it, and I'll plop that. Oops, I guess we should look at something first. Yeah, well, I've specified the relationship between tangential acceleration and angular acceleration, but let's look one more time at whether something is speeding up or slowing down. So something also to note, this is one of the more subtler points in this discussion, is that tangential acceleration is a signed quantity, SIGN. Sometimes it's positive, sometimes it's negative. Just like velocity, right? If you're looking at the velocity, let me back up here. We know that velocity is a vector, right? But remember in the early part of the semester when we talked about just motion along a single axis, if you're just looking at one-dimensional motion, your velocity can be positive or negative. That's kind of what we're doing right now. In this graphic here, the velocity we're talking about is along the tangent axis. So at least at that instant in time, it's kind of like one-dimensional motion. You're either moving this way tangent to the circle or that way tangent to the circle. So there is a sign, SIGN, associated with it. And that's also going to be true of the tangential acceleration. So here is the rule again. Actually, I shouldn't say again because this is the first time I've pointed it out. Remember back in high school when you took pre-calculus, perhaps, or college, we measure angles positive in the counterclockwise direction. Right? If you're tracing out an angle in this direction, that's a positive angle. And for that reason, a velocity that points in the counterclockwise direction, tangent to the circle, that's considered a positive tangential velocity. So in this picture, the tangential velocity is positive, so is the tangential acceleration, because it also points in the clockwise direction. So they're both positive, and we concluded previously that if that's the case, your particle would be speeding up. If it's got an acceleration in this direction, that would require something to push it in that direction. If you push on something in the direction that it's already moving, you will cause that thing to speed up. What about here? Well, we can see that the acceleration, the tangent acceleration, is opposite the velocity. That's like pulling back against something, pulling opposite the direction it's moving. We would expect it to slow down, but notice in this case, because the tangential acceleration is clockwise, we give it a minus sign. So this is the pattern to note. When a sub t and v sub t have opposite signs, your particle's slowing down in its circular motion. I'll go back a slide. When they have the same sign, your particle is speeding up. Same sign, speeding up. That's true even if, let's look at this example, what about if both of those things are negative? So if the velocity, if the tangent velocity is, notice this is velocity at some time t. You know, I probably should have called it v sub t just to clarify, but they're both valid. This was just from the previous slide. I was talking about the velocity at some particular time t. But this velocity vector points clockwise around the circle, so the tangential velocity would be considered negative. So too is the tangential acceleration. Even though they're both negative, we're still speeding up. Because if you're pushing something in the direction it's moving, you will cause it to speed up. So just because the tangential acceleration is negative does not mean you're slowing down. This is the difference between the precise language we use in physics and the way you might talk about it casually outside of a physics class. Usually, if people are considering a negative acceleration or a deceleration, we think that means slowing down. But in this class, that's not necessarily the case. If your acceleration is negative, you may be speeding up. The significant fact is whether the tangential velocity also points in the same direction or the opposite direction. So let's collect those three results. Just like some of the other equations we've looked at, this might be worth tattooing on the back of your eyelids. At this point, you're probably running out of real estate, because I've said that a couple times, but you are going to use these equations many times between now and the end of the semester, especially when we get to rotational motion and torque, rolling motion. You will actually encounter these formulas in a different context where they really mean something different. Because right now we're just talking about something that's spinning, like a point on the equator of planet Earth as Earth rotates. Later we're going to talk about spheres rolling down ramps, hoops rolling down ramps. We'll talk about pulleys with ropes wrapped around them and something unraveling from the pulley. And in those contexts, these equations will also pop up. So it's worth memorizing these now. And it shouldn't be difficult, because look at how they work. In each instance, you take an angular quantity. This is just angle. This is angular velocity. This is angular acceleration. You take that angular quantity and you multiply by the radius of the circle, and you get out what is often called a linear quantity. That's it. So you plug in an acceleration here, you get an acceleration out. Plug in a velocity, you get a velocity out. Plug in an angle, get a distance out. Look at the dimensionality here, for instance, with tangential velocity. The left side here, tangential velocity is measured in meters per second. So I've indicated the dimensionality there. Radius is a distance measured in meters, and angular velocity, remember, a radian per second, that's really just an inverse second, because the radian is already dimensionless. So when you see s to the negative 1, that's 1 over seconds. Inverse seconds is the same as radians per second. But notice how the units are consistent? Meters times 1 over seconds is meters per second. So the dimensions of these angular quantities multiplied by a distance, the radius, will give you the appropriate dimension for the output. That should make it easier to memorize when you notice that pattern. Same thing for the relation between the two accelerations here. Angular acceleration, that's the rate at which your angular velocity is changing. So it's like, how many radians per second is your speed increasing by per second? How many radians per second per second? Hence the units radians per second squared. So that you can think of this as radians per second, but the radian is dimensionless. When you take those inverse seconds squared and multiply them by distance in meters, you get the appropriate units for linear acceleration. We already know that linear acceleration has units of meters per second. So observing the relation between the dimensionality of both sides should help you memorize these equations. And I guess now it's time to do a homework problem. So let's take a look at the problem. This is number 76, chapter 4. Ooh, it's a 3-dot problem. We should be scared. Those are supposed to be difficult. We've got a car they say on a curve with a radius. Well, I suppose that means a circle. 120 meters. They give us a tangential acceleration. Great, we just looked at that. A very modest acceleration of 1 meter per second. What does that mean? Every second that passes, this car speeds up in the direction it's moving by 1 meter per second. Through what angle will the car have traveled when the magnitude of its total acceleration is 2? Okay, magnitude of its total acceleration. Well, we've seen that the total acceleration vector has components. There's a tangential component and a centripetal component. So we've got to worry about both. The tangential acceleration is always there, presumably, and because we're moving in a circle, there must also be a centripetal acceleration. Here's my lame drawing. I've written down the information that we're given. We're told that, well, you know what, let me start with the 2 times. I will call the time at which the car begins accelerating t0, and that's 0 seconds. t0 equals 0 seconds. And then at some time t1, as they've made their way around this circular track, they will reach a point where their total acceleration has a magnitude of 2 meters per second per second. So those are the two relevant times, the most obvious labels, t0 and t1. And then we're told that the velocity initially is 0. So I've said v tangential initially is 0. And remember, it's a little unnecessary to say v tangential, because if we're moving in a circle, then v tangential is the only velocity. But we'll be consistent with the notation here. Again, the problem states that this track has a radius of 120 meters, and we've got this modest tangential acceleration. Okay, so let me make a bigger diagram here. Here's the circular track. Maybe they started here, but at some point over here, they've gone fast enough that, or they've gotten fast enough that, in addition to their velocity, which is tangent to the circle, they've picked up, yeah, now I'm realizing this is going to be cluttered. Okay, let's think of this actually as the tangential acceleration, although I like to make that dotted, don't I? Okay, I'll just kill another tree, no problem. Circular track. Okay, there's the ever-present tangential acceleration of 1 meter per second per second. But because they're moving in a circle, there must also be a centripetal acceleration, and then I'll use a pen to draw their velocity, which of course is tangent to the circle. And I should really have a straight edge here. I'll draw a short velocity. Okay, remember, the centripetal component or radial component of the acceleration, which points towards the center, is v squared over r, and I'll use capital R because that's what I chose to write in the diagram over here. They're going faster and faster all the time. Tangential acceleration, remember, is the time derivative of tangential speed. And we're told that this number is 1 meter per second per second. So they're always getting faster and faster. Now, as they get faster, as v increases, v squared over r will of course also increase, which means their centripetal acceleration increases. The faster you're going around a circle, the greater that acceleration has to be. So over here, they still have the same tangential acceleration. That's always 1 meter per second, because that depends on how hard you're pushing on the gas pedal and the friction between your tires and the road. So that has not changed. Tangential acceleration is the same as it was before, same length. But because they're now going faster, which I'll indicate with a longer velocity vector, see how the length of the velocity vector has increased from here to here? Now they're going faster. As a result, they will definitely have a longer centripetal component. And I meant to finish this. These are the two components of the acceleration. So the net acceleration here is this vector. The overall acceleration has a tangential component and a radial component. At this later time, the tangential component has not changed, but the radial component or centripetal component certainly has changed because they are now going considerably faster. So if I draw the resultant of this component and this component, that should end here. So this is the net acceleration. And you can see it's definitely longer than it was at the previous time. So as this particle, or as the car moves around the track, this component is changing direction so that it's always tangent to the circle, but it doesn't change its length. The centripetal component, or radial component, is also changing direction. Here it points that way, here it points that way, but it's getting longer because its magnitude depends on the square of the speed, and we know that the speed is increasing. Why is the speed increasing? Because of this tangential acceleration. If you push on something in the direction it's already moving, it's going to speed up. So you see that this vector is going to get longer and longer, and at some point, this vector will have a length of 2 meters per second per second. You can see I didn't draw this to scale because if this really is 1 meter per second, then here we've already exceeded an acceleration magnitude of 2. But hopefully you get the picture. Okay, so how do we go about doing that? Well, remember the Pythagorean theorem, or the formula for Pythagorean's theorem, will tell us what the magnitude of the overall acceleration vector is in terms of the components. So we'll use the fact that the magnitude of the net acceleration vector is the square root of a sub r squared plus a sub t squared. Now what your solutions manual does is to plug in the number 1 right here. I could do that. I'm going to try to do things symbolically for now, but in this problem a sub t is just 1, which would make it easier to write because the number 1 is easy. We also know that a sub r that's the centripetal acceleration, that's v tangential squared over the radius. Now I'm emphasizing that the velocity in question is that tangential velocity. So I could take this and plug it in there, but what is the tangential velocity? And here we come to something that I probably should have developed in this presentation, but I did not. So I'll do this off to the side. Remember this equation for one-dimensional motion: final velocity is initial velocity plus acceleration times time interval. You've seen this, whoops, I should say v sub I. We'll use that notation. V final is v initial plus a delta t. When is this applicable? If the acceleration is constant. That's the constant acceleration kinematic equation for how the velocity depends on time. We can apply this equation to this problem because the tangential acceleration is indeed, where's my picture go? Oh, it's right here. We're told that the tangential acceleration is a constant. So even though the tangent axis is changing, we can still analyze the motion along that axis as we would for the x-axis or the y-axis. So let's apply this equation to the velocity along the tangent axis. V tangential final would be v tangential initial plus a tangential delta t. There it is. It's this equation applied to the t-axis. Just imagine, at any moment in time, if you're in this car, the axis you're talking about is the one that goes straight out ahead of you through the windshield. And yes, the direction of that axis is turning, but you can still use one-dimensional kinematics along that axis. And since our acceleration in that direction is constant, we can use this constant acceleration kinematic equation. Now, it was already specified that the tangent velocity at the initial time is 0, so that's gone. And delta t would be final time minus initial time, and I chose 0 seconds to be the initial time. So I can just rewrite my delta t as t, and that means that the tangential velocity at any time is just whatever the tangential acceleration is times the time. So if you've been picking up speed, that's supposed to be a t, at 1 meter per second, and you've been driving for 5 seconds, you are now moving at 5 meters per second. That's how we express the speed in terms of the tangential acceleration. So take this and plug it in there, and we find that the radial acceleration, well, if I square this, I get an a sub t squared over r. So the expression for the radial acceleration can actually be written in terms of the tangential acceleration, just for this problem. And then, check it out, we have to take that and square that. So we really pick up a t to the 4th, a sub t to the 4th. Let's do that over here. You can see how it's kind of messy to keep all the symbols here. Okay, so the magnitude of the net acceleration is the square root of, let me take all this and square it, and then I get an a sub t to the 4th, t to the 4th over r squared plus a sub t squared. Not a pretty expression, not worth memorizing. It's only applicable to this particular problem. You can see that the overall magnitude of the acceleration has kind of a complicated dependence on time. Before I plug in numbers, I also want to point out, you see how when we're not going very fast, the net acceleration really doesn't point towards the center. That would be a purely centripetal acceleration. This has been pulled away from the centripetal direction. But the faster we get, the more the centripetal term dominates compared to the tangential term or tangential component. And so this net acceleration vector starts to slowly bend towards the center. It will never point completely at the center because this doesn't go away. Of course, in real life, you stop accelerating at some point. Your car can't just keep getting faster and faster. Okay, let's now plug in the fact that A sub t is just 1 meter per second, and that will make this look easier. And I might as well plug in the 120 meters as well. So the net acceleration would be the square root of t to the 4th over 120 squared plus 1. We're looking for the time at which this acceleration reaches 2. That's it. As you keep driving, you get faster and faster. Your a vector gets longer and longer. What's the point at which it reaches a length of 2 meters per second per second? Okay. Set t equal to that time that I labeled t1, and that's when the net acceleration needs to be 2. Okay, so 2 must equal the square root of t1 to the 4th over 120 squared plus 1. Do you see how efficiently I'm using the paper here? How do we get t by itself? Let's square both sides and do a subtraction. So I'm doing a couple steps at once here. I find that t1 to the 4th over 120 squared should be 4 minus 1. See, I squared both sides, I subtracted the 1. And that means that t to the 4th should equal, well, this is 3. What's 3 times 120 squared? 120 squared. You know what happened? This thing is sitting next to my kitchen sink, and when I wash dishes, which is not often enough, sometimes the soapy water gets in here. Now my keys are stuck. But I'm not throwing this thing out. This was a $10 Casio that I got in 2007, and I don't want to lose it. 120. I used to lose calculators all the time, and one day I got so mad at myself for wasting money like that, I resolved to never lose a calculator again. And so far, hasn't happened. Okay, let me check that. 120 squared times 3, 43,200. And we're taking the 4th root of that, right? T to the 4th to the 1/4 is just t to the 1st. I'm undoing the exponent of 4. So 43,200 raised to the 1/4 power. On my calculator, I would use this exponent button, and then I'll just type in 0.25. That's the same thing. And I get 14.4 seconds. Is that the right answer? Let's check the book. Oh, yes, 14.4. And you know what? They're not actually asking what time it happens at. They're asking what's the angle through which we've turned. Ooh. And you know what? For that, we have to use rotational kinematics, which I have not yet introduced. So I might leave that part off of the problem. But let's just check something real quick. Let's check. The tangential velocity at 14.4 seconds is tangential acceleration times 14.4, right? Just take the 10 meters per second times how many seconds we've been accelerating for. Did I say 10 meters per second? It's 1 meter per second. So that's just 14.4 meters per second. That's how fast the car is moving after driving for 14.4 seconds and speeding up every second by 1 meter per second. And then the radial acceleration would be v tangential squared over r. That's 14.4 meters per second squared over 120. So what is our centripetal acceleration at that time? 14.4 squared divided by 120. I find 1.728. I'll keep a few digits. And now let's use Pythagorean theorem. That means that the net acceleration, well, that would be the square root of 1.728 squared plus the tangential acceleration squared, 1.0 squared. Okay, 1.728 28 squared plus 1, hit equals, take the square root sign. Not quite 2, but that's, of course, rounding error, 1.996. That's basically 2 meters per second per second. So it seems to have worked out. The algebra that I did was correct. Now, as far as figuring out what the angle is that the car has turned through, well, I really ought to develop this in more detail, but if your angular acceleration is constant, you can use an equation to find the angle turned through at any time that looks exactly like the constant acceleration kinematic equation for displacement that we've been using. Remember, delta, your book likes to say delta S, some arbitrary axis. V initial, delta t, plus 1/2 a delta t squared. You can only use this for constant acceleration. Well, instead of talking about a displacement along a line, a linear displacement, now we're talking about an angular displacement. What's the angle that we've turned through? So your delta S becomes a delta theta. Instead of initial linear velocity, we're talking about initial rotational velocity. So that would be omega initial delta t. And instead of linear acceleration in a line, we're talking about angular acceleration. What's the rate at which your angular velocity is changing? So that's 1/2 alpha delta t squared. This is what we're being asked for in the problem. So as this car is going around and around, what's the total angle it's turned through? How many radians or degrees, whatever, due to that constant acceleration? Okay, so now we can use one of the equations that we did look at in this presentation. First of all, I'm going to recognize that for this problem, we can cross that out. The car starts from rest, so it has no initial linear or angular acceleration. Now, remember that linear tangential acceleration is radius times angular acceleration, right? You start with the angular quantity, which is in inverse second squared. You multiply it by distance in meters, and you get meters per second squared as needed. Right now, we're solving for alpha. So alpha would just be a sub t over r. In this problem, the angular acceleration would be that 1 meter per second per second. Sorry, the 1 meter per second squared divided by 120 meters. And you see how the units work out? The meters cancel, and we do get inverse second squared. In other words, radians per second per second. What's that in decimal form? 1 divided by 120. 0.0083333333. Okay. So now that we know the angular acceleration in radians per second, we could plug it in here, and we know the time already. We solved for that. So delta theta is 1/2 times this rather small angular acceleration. I could have just left that as a fraction. And my delta t we found was 14.4 seconds. Okay, we've got a small number and a rather big number. That should sort of cancel out, 14.4 squared. And I'll divide by 120, which is what we're really doing, times 1/2. 0.864 radians. 0.864 radians. Remember, if you plug in SI units, or let me rephrase, it's not, you don't always have to use radians per second here. It could be degrees per second, but then you have to make sure that your other term also uses those same mixed units. So when it comes to rotational kinematics, the safest thing is probably just to stick with everything in radians, meters, and seconds. Use SI units. But if I want to convert, remember 1 radian is about 57 degrees, so let me just use that conversion factor. That's approximate. There are about 57 degrees per radian. Basically 49 degrees, or even 50. What does your book say? 49 and a half. Okay. So the one part of this problem that might seem a little out of left field is the rotational kinematics part. But hopefully you were able to follow everything in the first half, which just involved the vector nature of acceleration, the two components, the Pythagorean theorem, the formula for radial or centripetal acceleration, which came from our geometric construction in a previous presentation. Remember, Newton is the one that gave us that formula. And then this just kinematic expression for how tangential velocity depends on a constant tangential acceleration.